for this one, and I would like to talk about few things uh, before we go ahead and looking into mainly chapter 10 homework and final exam. Today is the last day of that one, and then we can take some terms and then finish pretty much everything. I think I saw something. I want a little bit. Oh, Thomas here. Okay. Okay. Okay, Thomas. Good evening. We just started. Okay. I just started. Okay. Then, but I was trying to do something. I think that yesterday a little bit. One question I read. I think this one. I would like to. I'm gonna share the screen. Okay. So this one, the one that when I was talking about the exclusive, I think here we had the less than sum of 4 and at least 1 5, because I was reading wrongly that one yesterday. I think it should be at least 1 5. That means at least 1 5, or it can have like a more than 1 5. So if it is at least 1 5, 1 and 5, see 1 5, see 1 5, 2 and 5, 1 5, 3 and 5, 1 5, 4 and 5, 1 5, 5 and 5, 1 5, or this whole thing, see, all these will represent the at least 1 5. This whole thing will represent at least 1 5 plus here 2 5s. 2 5s are okay too. 2 5s are okay, but it's been repeated twice. That's why we have 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. At least 1 5. 1 5. The other one, some some less than 4. Some less than 4 means like a not equals to 4. No, not this one. Yeah. I was reading now that it's like a kind of optical illusion, even though that is very close to me, that I read wrongly. Some of them, that means 1 and 1 less than 4, 1 and 2 less than 4, 1 and 3, no, only this one. And then 2 and 1. I'm talking about this part, not this part. These three. That's why we have 3 over 36. For that one, then what we were trying to say, those two events, not gonna say they don't have this event as well as this event. Okay, the down one with 3, not this one. That's the one that I showed you yesterday. It was a mistake that I was reading wrongly. So this one, these 3, and here that one, at least 1 or 5 from this grid, you can easily get that one. And that's, they do not intersect each other. They do not intersect each other. That's why we call it mutually exclusive event. On the other hand, here the same thing again. We were talking about at least 1 6 this time. At least 1 6, at least 1 6, or 1 6, and here 2 6 are here. It can have like at least 1 or 2 or more than 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See, it's been repeated twice. You're not gonna put this one twice 11. And sum is less than 11. See, less than 11. See, 6 plus 1 plus 6 less 2 plus, see, less than, see, 2 plus 6 8, 3 plus 6 9, 4 plus 6 10, 5 plus 6 6, no, 11. It's not, should not be included. So then 11 5, 6 plus 5 11. See, 5 plus 6 taken out, 6 plus 5, and for 6 plus 6, these 3 were taken out. That this bigger one for sum less than 11, these small pieces are at least 1. When you put together, they would pretty much cover the whole thing. That's called the sample space. If that's the case, we're going to tell that those events are exhaustive events. That's the one that I want to bring to your notice. I think I made a mistake yesterday, especially on the other page. Okay, so that's that. Let's get out of that one. Let's go ahead and look at this one. We can remember yesterday when mainly that we are planning to Go through chapter 10, homework 4, and final exam. Okay, that's the major thing that we are planning to do today. Today is the last day. We are planning to cover pretty much everything. Okay, so in this one, while I was going through, in addition to this one chapter, this homework 3, can you remember under the fish, we were talking about all possible selections at a certain point. At a certain point, we couldn't run Akaike yesterday. See, Melos it worked, but the Akaike cannot run. See, look at what's going to happen. This is exactly what happened yesterday. I was trying to run Akaike information criteria for this one. Let me see. I'm going to run this. Get the data first. Fish data. Okay, just in case. Okay, and then do this adjustment. And then now it's going to be in work directory. It's not been put into the work directory. There's another one other step here. At this stage, I put that into the work directory. Early, it was in SAS help directory. See, in the beginning, it was in the SAS help directory. I got that one in SAS helps. Set means like you're going to take it and put it back into a new one called the work. Okay, I didn't do that one. So now it's in the work directory. That's the directory now I'm using. Okay. So get the love. See, I'm working with the work directory. This one is I'm working with the directory and put it back into work directory again. Data means not the data. Okay, set means the data, current data. This is the current data. This is the data to be utilized. See, this is the new name for that data frame. So we run this one to. Okay, then all the changes are here. You know that once they came into the picture. And then especially then I was trying to run this Akaike. See, Akaike, this one, it didn't work. That means that this is syntax are expecting one of the following. This one, this one, this one, this one, this one, this one, or this one are required for that to go along with that one. Otherwise, it won't work by standalone. See, that means I'm going to put edge adjusted square, no? Adjusted R square, is that the right one? Adjusted edge RSQ, sorry, edge R square, edge R square, and then run. Then it runs. Akaike information. I just asked for that only the they give me the two best ones. See, that's why it's gonna give that. It's gonna give me adjusted R squared, and Akaike. See, so with that one, I'm gonna go to the smallest one if I'm gonna stick to that one. So just in a similar way, Sava had the same issue. You have to put some kind of a criteria go along with that one in order for that to run. So, okay. It's pretty similar to the Akaike. Sava is then some kind of a modification. It's a modification for the this n times ln SSE divided by n. See, instead of 2k, what he did was he just make some kind of adjustment for this constant. That's it. Then let's say the press. Let's see press. Yeah, press works. Okay, then best 2 S2 press. That means that prediction sum of squares, it's going to go along with the adjusted R square and press. That would show only the adjusted R square. R square they're going to take as a like a this is like a adjusted prediction sum of squares is they're going to take as this one R square. So I don't why I don't see that one particularly. That's the one that going to represent that one. I just put the adjusted square and the press means like at this part for the whole data set. But as I mentioned, that's not the way how we should do this one. Because for the press, you are not supposed to use the whole data set. You know that one. You know that one. I mentioned here very clearly data should be split and then run the press. Okay. Here say the size of the fitting sample, or it's called the training sample. Can you remember fitting sample or training sample? Fitting or training sample. For this one, fit the possible base model for the prediction of forecasting. Then the N2, I'm going to get the data set and split into two parts. The sample size of the holdout sample, testing sample. One is training sample, the other one is training sample. So in order to get this done, how to divide that this given data set into two parts, training sample and then testing sample, and the testing sample is the one being utilized over here. Otherwise, that's why press becomes R squared. Press and R squared the same if you're going to use the whole data set. You're not supposed to use the whole data set. You're supposed to use only as I shown yesterday, even on this one, you can remember that's the same thing. You can remember. See, I'm going to get the data and split into two parts, training sample, training data, fitting sample, which is N1. The other one is testing N2. Under that one, I'm calculating MAD, map, those kind of things. And even that press to press press one, let me see the press one. Yeah, the best thing to like that we can run that with the press, but it's okay. So sometimes it's okay, but sometimes it's so not okay. But best thing to get the training sample, mainly for that SPSS and the MAD. See, okay, then these three. Sorry. See, mean square deviation MSD, mean absolute deviation MAD, mean absolute percentage MAP, and those three can be calculated for sure. Those three for sure using the training sample. How do you pick a set, split the train? See, split, train, and test data set in SAS. You are using what? Random uniform numbers. Method one, random uniform. If you have a uniform distribution which has like a numbers, which has a numbers between 0 to 1. See, 0 to 1. See, the random ran uni function returns random variable between 0 to 1. This is called the lower bound. This is called the upper bound. It's a function that returns a pseudo random number generated from the uniform distribution. So it's the uniform distribution, you know how this uniform distribution is. Then uniformly they were distributed between 0 and 1. All the distributions are sprung from uniform distribution. So everything here, see, if you have an X here, you have a percent, or you can have the relative frequency, rel frequency here. So you have a 0 to 0 here. 1. That's the uniform distribution. It's a uniform distribution, uniformly distributed. So uniform, remember, continuous uniform distribution, continuous uniform distribution between, we normally denote like this, say u between 0 and 1. So this height is nothing but this is 1, this is 0. Normally we call this one A, this one B, lower bound. See, this one is nothing but 1 over B minus A. In our case, it's going to be 1 minus 0, which is 1. So area under the curve is 1. This is 1. This gets is B minus A, which is 1 minus 0, 1. This is 1 times 1, which is 1. Therefore, it's a PDF. 1 times 1. See? 1 times 1. It's a rectangle. So uniform distribution. So we're going to generate the numbers between 0 and 1. See, 0 and 1. These are the numbers you generate. See, you generate the numbers here. From here. See, 100. See, 100 numbers you generate. 100 numbers you generate from there. See, that's what we're going to do in this method. See. So you get the fish data. You're going to generate 100 numbers, see, random numbers, and put it to temporary this month, and you're going to sort it, see, by n. See? Okay. See? N is the any value between 0 and 1. See, 0 and 1. See, 0 and 1. 100 of them.
I just want to make sure that I understand what we're getting. We're doing the split train method, right?
Yeah, split training method.
Okay.
Yeah, I'm on a split one. I'm writing the code for how to get that N1 and N2. I'm sorry.
Okay, so right now you're what you're doing is splitting the data between data that is trained, or the data that we're training on, and data that we're testing on.
First one is I'm doing a training, and later on I get the both. That's why based on this percentage, we're gonna decide.
Yeah, and we're gonna choose everything that's 0.75 and above as test, and then everything below as train. Exactly. And that's how we'll split our data set, since we're not doing like it's not like an A/B finish.
Yeah. See. That's okay. Right. See. That it depends on that. Okay, you're gonna say split the data into 75% training and 25% testing. You decided that one.
Okay. Got it.
So based on that one, in order to do that one, you're going to do based on this one. See, but you have 100 data. You don't need the 100 data fitting into our data set, because the data set doesn't have 100 data points. Can you remember? It has, see, it stopped here. See, I think it has, sorry, no, the other side too. How much we have? 100. Oh, we have 159. That's okay. They can randomly generate. Yeah, that way it's okay. It's not a big deal. I mean, like you get the 100 number, you reshuffle and then generate again and again and again, and that number pick, and then it seems like a same number can be picked, but it's more than enough to that tackle this whole thing. Yeah, whole thing. See, that's okay. If you if you feel like that, if you want, you can get the 200 numbers, so the same number of numbers. But
so in this step, we're just labeling each data. We're just labeling each row with a value. That's
exactly. We just simply say that okay, there's just okay. We're gonna assign a certain value for that one and say, hey, whatever that it seems like we are labeling, as you said, that label, and then randomly we're gonna pick 75% gonna go to training, which 75 gonna go to the training. That's why we're gonna label first, as you said. Yeah, that's perfect. Right. We are labeling. At the labeling, and then we're going to say, okay, set that, go to the temp one, and then no observation to see if n is less than 0.75. See, then the times, the no observation, see, number of observations, see, 75% sometimes the number of observations. See? Number of observations. See? See? And then we're gonna have a, we know the number of observation is that the sample size, from the sample size 75% gonna go to training, the other one gonna go to that one, but we would just label as you said that in the beginning. And when you do like this, see, it still doesn't have anything here, so we're gonna see the pretty much the same thing still. But if you go ahead and get the print those two separately, you can see that which one's gonna go to the testing, which one's gonna go to training. It's a training sample. The second one would be the testing sample. See, this one has 119, this one has a 40. See, that's one of the way of getting this done. Okay. So you can see here clearly that with the thing, that label, we utilize that label to that separate them, that anything that less than 0.75 gonna go to the training. See, training, else you go to the testing. Or second method, you can use this procedure. See, split train and test data set into SAS proc survey select method 2. Step 1, use the proc survey set and specify the ratio of split for the train and test data. 70% or 30% in our case, let's say like that, 70 or 30, along with the method in which SRS stand for the simple random sample in our case. See, it's a ratio, 0.7. That means like which one's gonna go to the train one, we're gonna mention over here. Okay. And we get the data, and then I'm gonna out that one called the fish select, and method is simple random sample method. See? Simple random sample method. Yeah, all the information, sampling ratio, see, sample size, see, thing over there. Then later on, I'm gonna go to the fish train data and fish test. Okay, the fish select and both. I'm gonna call these. Those are, one is fish train, the other one fish test. Both I'm trying to get the both. Fish select, get this one, and if this selected equals 1, then output gonna go to train. You see 1, it's gonna go to that one because I call that one. See, if selected, it's the selected equals fish select data survey select data fish. Okay, this one, okay, out fish select, and this one selected equals 1. Yeah, then it's gonna go to this one, if not gonna go to the other one. Okay. But they don't have anything over here, then let's print these two. It's another way to get that train data. And that's this one 47, 112. Earlier what we got, they were randomly saved there, they were randomly assigned to those things. Okay, those training and then testing samples. $119 and $40. $117, $112 and then 47. That is pretty close. Okay, they were pretty close. And then on the other hand, on the same percentages, we are not using the same percentage. We were using the different percentage. See, point, if you use the 0.75, let's use the 0.75, 75 and 25. That's for those are for the ones. Oh. Okay. Okay. Then get 39, 120 and 39. Pretty much the same thing earlier. Pretty much the same. Yeah, you can use the one of these method to in order to get the data splitting. Okay, then you're gonna calculate this one based on that N1 and N2. So N1 for that train data, N2 for the testing data mainly. Then we can calculate that one, and let's see that, and you can run that one and then see that whether we're gonna come up with these ones too. Okay. So I'll get back to this one that, okay, this one, but the same way that again that when once you've done that one, when you discuss about the MSD, MAD, those things that when you evaluate, later on you can, again, I was showing that instead of going to selection forward and backward, you can get it done at the same time with the one function, see, one procedure, GLM select procedure. That's related to that one. That's that one. Number 3, then chapter 10, we were talking about the discriminant analysis the other day that we just ran this one, we get the answers, see, can you remember? Then we were talking about the principal component analysis, and then we were talking about the factor analysis. How could that, what do you mean by that, the factors, factor analysis, what do you mean by factor analysis? What do you have in factor analysis? Principal component analysis and factor analysis. So pretty much that, let's say that related to this one, what I'm gonna do, I'm gonna run this one and show you something. So in the factor analysis that you are trying to write the current variable in terms of the latent variable, in terms of the latent variables. Okay, some latent variables. Can you remember that we were talking about in this related to, I'll show you that there was a test. That one. Test oh, here, okay, factor analysis and principal component can kind of like doing the same thing. They were doing two things: the dimension reduction plus unnecessary really the variables are taken out. They both are done. Okay, so okay, look at it. See, let's say that example that students taking 4 exams: English exam T1, German exam T2, math exam T3, physics exam T4. So specification, see, English specific skills, that particular person. Common factor is what? What is the common factor? Language ability. Some person has a language ability. Even within the language ability, some person is really good in English, some person not good in but another way, and vice versa, or the other way around. So these are specific factors. These are common factors. So specifically that he is really good in English specific skills, German specific skills. that common factor. There's another common factor, technical ability. Even with that one, some people really good in math, some people really good in physics, some people really good in both. Doesn't matter. Okay. We expect two underlying factors, language ability and technical ability. See? See? So if you have a principal component, what you're gonna do with the aid of this current that variables, these four variables, you're gonna write the new components to reduce the dimensionality rather than working with all these four exam in order to assess that somebody to be accepted to like a law school, medical school, or graduate school, or to any job or anything like that. They have given this exam so that or their undergraduate program or anything like that. Okay, rather than just taking into account all these four, we are trying to we were planning to reduce the dimensionality, and then some unnecessary variables that's going to affect to that maximize the variance. See, that means find the best component who will maximize the variance. So that's why we are writing the principal component. See, so you have a T1, it's been weighted by its loading. See, loading. See, loadings. Can you remember? See, and PC2, another loading, different kind of a loading. See, these loadings, you can remember these loadings. They were nothing but the eigenvectors. See, you can write the four principal components for that guy. That's a PCA. In addition to PCA, you can do something called factor analysis as well. Look at factor analysis, FA. Estimate the specific factor and common factors. That is two common factors in this case, language and technical ability, and form four specific factors, ability on test 1, test 2, test 3, and test 4. That are explained by the language and technical ability under that one. See, you have a four specific one. See, four specific abilities and two common abilities, and then same person, one at a time, who's taking the test 1. When you go to take a test 1, which is that we say the English exam, you still have the common ability. Common ability, under that common ability, we have a two common abilities, technical ability as well as language ability, plus specifically that English language ability. See, look at it. So you're not gonna write you're not gonna write the way that I did for the principal component. In the principal component analysis, what I did was that I utilized the existing variables to come up with the new variable. Here, not like that. I'm gonna come up with the new variable and unmask this guy, being unmasked, and see who are the responsible for getting a good grade or bad grade on this particular test. See, I'm unmasking. When I'm unmasking, these are hidden variable, hidden latent variable. See, hidden variable, lurking variables that's going to affect to the grade of that particular test. Those are unmasking. So we're going to assume that with the aid of these the hidden variable, if you can write this one, then you can easily come up with proper gauge about that the ability of that particular person at the end of the day. That's why we're going to add the two common abilities. They were being weighted to. Those are called the factors. The eigenvectors. Those eigenvectors again, and this is specific. Then you go to the test 2. Again, you still keep the same thing. K1 and K2. K1 and K2 stand for common ability. Ability in language, ability in technical subjects, plus ability in German. See, this is a German exam. Third exam, you are taking, still you carry that two abilities. See, you have that ability. Common ability, you will still carry. Okay, then that one, that certain being weighted, certain amount being that utilized in order to put the weight. But and the third one is the ability in third exam, let's say math skills, gonna come into the picture, specific ability. The fourth one is nothing but the physics test. So still you keep the language ability, technical ability. On this ability, you have a very specific ability called the D4 as well. See, In factor analysis, you're gonna write the same thing being written in terms of the latent variables. In principal component, you wrote that one. Get the principal component, you wrote. Okay, compare and contrast. You write the same test are being utilized in order to the dimensionality reduction. And then you are looking for the best component who maximizes the variance. That means even over here, according to the Kaiser rule, that's the Kaiser rule, you're going to go to the principal component with the eigenvalue more than one. That's called the maximizing. Some of them are dropped. Get here. Here it's other way around. You're going to see that how this variable being generated or how this being composed of what kind of a hidden variable. So on the other hand, when you have a principal component analysis, when you run, you get some results. On the other hand, you get when you run the factor analysis, you get the result. From the factor analysis, you can come to the principal component analysis. Let's see how that can be done. Okay, so how that can be done. This principal component analysis. That's what I was talking about. The picture. Let's say related to chapter 10. Okay, chapter 10 and the homework for pretty much the same thing. Okay, so you have the data, you have this data, trained data. Okay, then you did the discriminant analysis. Can you remember discriminant analysis? You easily figure out. Okay, see test 1 and test 2. Based on that one, how they've been classified into two groups. You had a two groups, so it seems like a two groups. You're going to classify to two groups. So discriminant analysis and logistic regression pretty much go together. Factor analysis and principal component analysis pretty much the same kind of like a procedure, but they different from each other, go together like a pair. And generalized linear model and regression model go together. So those three with like a 6 aspects, but those three, all these 6 like come like a 3 combos and then work separately, but like a pairs. So when you can do something, you can compare and contrast the discriminant analysis and logistic regression. You can compare and contrast. You might be thinking, why I'm not going to use the discriminant analysis when you have used the logistic regression. Logistic regression, you know the reason when you have some kind of a violation of that normality assumption for the regressive variable, not the error, regressive variable. Or if you are using the categorical variable for regressive variable. Y variable definitely categorical. You can use the logistic rather than discriminant. When it's come to that GLM and reg, GLM gonna talk about the most general that model rather than just narrow down linear model. They're gonna talk about the general model, which can tackle whether that your Y variable, Y normally distributed or not, error terms are normally distributed or not, whether you have a other kind of distributions, let's say Poisson distribution, gamma distribution, binomial, inverse gamma. Still, you can use what that regression you can run if you're gonna run the procedure that GLA. In the regression part, it's gonna very narrow down to very limited that area of that regression only, but it's not going to talk about the general linear regression, because the general model is tackled by the generalized linear model. In a similar fashion, that principal component and factor analysis you saw, you can compare and contrast. Okay, maybe. So in here, I think we did the discriminant analysis yesterday. Yeah, later on come back and do this one again. But logistic one we did too. The principal component we did, but what I'm trying to do over here, I will try to show you something. Come on. Sorry. GSP. different data set. Sorry. Okay. So now that data set, let's run the principal component analysis. See, now you have the data. See, see, even scree plot, you can easily say that how many variables to be kept. Everything more than one, 2, 3, 4, 5. 5 principal component we can keep easily. That means print 1, print 2, 3, 4, 5. That's it. These are the major ones. That's why I just keep this one 5. If you want, you can run 5. See? But you don't know until you're gonna get this done, because if you know the eigenvalues, you know eigenvalues even. Then you go to the fifth one. It's almost covered at 80%. If you're gonna round to the next decimal place, 80% of variation being explained by the total variation is by all these principal components. So when it comes to this number, look at this number. This is nothing but how do you gonna write the principal component one the way that we did over here? Yeah. So PC1 is nothing but 0.134820 AG plus 0.46970 700 mining times mining, and this time 0.035 blah, blah, blah. This is the eigenvectors all the way up to this one for the first principal component, second one, third one, fourth one. Okay. So let's say that the same thing, okay, when we know how to write, only 5 variables principal component will be kept based on the Kaiser rule. Okay. So let's go ahead and run the factor analysis. Factor analysis. We were looking for those scores. We were looking for the simple descriptive statistics and the correlations. Okay. Factor. Let's see what's going to happen. Yeah, these are the mean and standard deviation called the simple ones. Okay, this and that their correlation too. And this eigenvalue stays the same. Eigenvalue stays the same. There's nothing different. Only different here. Look at factor means PC1. Earlier we have print 1. Can you remember? If I run factor 1 along with this one, sorry, okay, run together these two, then I can compare. I'll show you something. First one for the principal component. I'm mainly interested in the eigenvalues are the same. So I'm well, see this one. See, these are loadings. Look at the loading. Look at the factor loading. The same thing. Look at they have another one too. See? Here they have been, see, 5 factor will be retained by the minimum eigen criteria. See, 5 of them will be stay over there. See, that's based on that Kaiser rule. They narrowed down to 5 factors. So these are the loadings too. But this time we're not going to go this way. We don't write this way. No. We don't write this way. We write this way. Factor 1 times 0.2 AG. Now you can write the AG. Okay. Now you can write AG. It's like this. Okay. So you see the same time this way. See, I'm writing AG, not the factor, not the principal component one, with the aid of the loadings. AG equals this fact 0.24251 times factor 1 plus this time factor 2 plus this time factor 3 plus this time factor 4 plus this time factor 5. We don't know what these factors are. Okay, we don't know which factors are. In our explanation earlier, we were talking about the technical ability, mathematical abilities, German, sorry, the language ability and all kind of stuff. The same way, some hidden factors. Okay, we write this way. So, okay, this is negative this way. And the mining, you write the same way, this way. Construction, this way, like that. So this is what I'm talking about. See, you are writing. On one hand, the variables are given with the aid of factors using the factor pattern table. Factor pattern table. I'm using the factor pattern table. That means this one, this table, not the second table, this table, first table. Okay, eigenvalue is the same thing. See, these are the loadings. I'll go right this way. I'm gonna write the AG agriculture. I'm gonna looking for agriculture, that one with the aid of other hidden variables. See, this to F1 factor 1 plus this to factor 2. See, then the same way government. But on the other hand, you can write PCs are given by with the aid of standardized one. See, if you want to write the PCs with the aid of this same thing, the factor analysis, you write this way with the aid of the standardized scoring coefficient. See, you're gonna say your PC1 is nothing but 0.07 times AG plus 0.2611 mining and so on, blah, 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 blah. That's the one I'm showing over here. PC1 you're gonna write with the aid of standardized one. Standardized one. See? This is PC1. I got the principal component analysis with the aid of factor analysis, but that's not the same thing if you go ahead and check that one with principal component eigenvalue, sorry, eigenvector. See, 0.13 thing, 0.13, 40, 20. It's not here. Look at here, under this one, not this one, the second one, 0.07495. See, 47095. That's why we are telling here, they're not the same. They're not the same. If you run that with the aid of the principal component analysis, you have principal component, we have 0.134820 for the AG. But with the aid of factor analysis, if you run that one, you have 0.07491. They're not the same. This is smaller. It's smaller. The reason is this one. It's the reason. Procedure factor and procedure printcom do not produce the same result. Okay, same results for principal component. Proc factors are approximately 1 over root 13 smaller. See, what is this one? This is nothing but that's the standard error. When you're going to get the standard error, you divide by what? Square root of the sample size. 1 over square root 13 smaller. Reason, procedure factor assume all factor components have the variance of 1, where principal component procedure assume that component have what? Variance equal to the eigenvalue. See? In the principal component analysis, printcom, if you run printcom, in that situation, they think that every component gonna carry the variance of eigenvalue. But if you run with the like a procedure factor, then it thinks like that all the factors gonna carry the variance of 1. That's the reason they're not the same. But we can remedy this one. I really need this value. This is the real value. But this is what I got through the factor analysis. Okay. Factor analysis gives this one. I'm just focusing on one value.
Close the door.
The rest would be taken care of the pretty much a similar fashion. How could we gonna remedy that situation? See? By doing what? See? By multiplying. See? I'm gonna use to get the standardized procedure and then go to the standardized procedure. See, standardized means that you're gonna divide by, see, you can remember. See, standardized, studentized, you can remember you have some kind of a estimator divided by its standard error. Estimator divided by its standard error. Pretty much a similar fashion, If you go to the method of the unbiased, uncorrelated standard deviation, that means when you're going to calculate the standard deviation, you're not going to get the standard deviation with respect to the mean. You're going to get the standard deviation with respect to the origin. That's why they call the unbiased. US standard deviation, unbiased standard deviation. Unbiased one. Okay. Unbiased means like, you see, you get the standard deviation about the origin than mean. But that means that when you can remember when you calculate any standard deviation, you can easily, standard deviation formula. Standard deviation is nothing but, okay, any standard. Awesome. Okay, while I'm gonna give this back, can just explain. You can open again. So what I'm trying to say that, see, I'm using this method, standardized method, an unbiased one, and then multiplied by the 1 over square root 13, which is 0.27735 as a that multiplication. Okay? Then you're gonna get the, see, all these variables, and then see, I'm gonna go to the GSP. See, go to the, this is for the factor analysis to PCA. I'm gonna get the GSP. You get the their loading scores, factor scores, factor scores, factor scores. And then I'm gonna go to the standard. See, standardized score of, I mean this one, this table. I'm referring to this table. This table. Go to this table. See, I'm gonna call that this table, that data, whatever the data inside, call the GSP coefficients. Those are coefficients. See, that's the name of the table. Standardized means STD score coef. STD, see, coef. So, I'll show you that here. What I'm talking about, that standard deviation. Unbiased means like a deviation. Normally we get x minus x bar square root of n. So this is about the mean. Instead of mean, what they have done, they squared this one and divided it. And no n minus 1. See, this is what they look at. This is about the origin. Sorry, about the mean. This is about the origin. You can get the standard deviation in any way you want. But here, then it becomes the unbiased. That's the one that we're talking about. On the other hand, what I'm talking about, this table, see, this table, this data, I'm going to call that data. The data, that's the one that I'm going to recall here as a data. See, okay, data means this table, this data frame. See, and then I'm going to get the whatever the value I have method, I'm going to use this method and multiply whatever the values. Whose values? These values by the 0.27735. Okay, 0.735. And run, and then I'm going to out that one and call that one eigenvectors. Those eigenvectors. Okay. Oh, I'm sorry, factor 30. No, not factor 30, factor 5, because we don't have 30. I'm not going to go to all the way 30, go to 5. Okay. Now you can easily see, look at it, see, 0.13482. No. Let's go and print. It's same as what you got from the principal component analysis. 0.13482. We didn't have that one when you run with this one. You can remember we had different value. I fixed that one by doing what? get the second from the factor analysis, you get the two table, one with the standardized one, the other one unstandardized one. Unstandardized one utilized for them to write their own ones. See, okay. So when you run the principal component separately, you get the same thing. See, principal component, if you run this one, you get the same thing. So that the PC one, the first number, keep it in head, see, 0.13. See, 134,820. That's how you're gonna remedy that. So if you get the factor analysis different, factor analysis, go to the run factor analysis, you get the factors. That means you're gonna look in for the factors, hidden factors that's gonna affect to the current variable. It's a different story. But if you really want to find that the principal component analysis through the factor analysis is the procedure. Okay. So keep in ahead, keep in these two, the comparison and contrast roughly, because it's all about the time, because within the short period of time that we've actually we covered a lot, because these are very broad areas, extremely very broad areas. We can talk about these its properties and this and this. Okay. So anyhow, that's the main thing that I want to keep you. I want to give you idea about this one. Fact analysis and this one go together, and logistic can this one pretty much go together, and the reg and GLM. Let's look at a little bit the GLM now. Okay, before we're gonna get to homework and then the other one. What do you mean by general case? The GLM. GLM. So in GLM means like a general linear model in which that it's gonna pretty much cover all the models, linear, non-linear, all kind of a model. Okay, all kind of models. Okay, let's go to this one. I'm gonna show this here. Okay. GLM. In statistics, the generalized linear model or general linear model, some people call the general, some people call generalized linear model. It's a flexible generalization of the ordinary linear regression that allow for response variable that have error distribution model other than a normal distribution. Okay. Statistical generalized linear model is a flexible generalization of the ordinary linear regression that allows for response variable that have error distribution model other than a normal distribution. To have that one, see? Allow for response variable to have any other variable which have like error variable to have any other variable rather than the normal distribution. Up to this point that we were talking about the normal distribution for the error terms. You don't need that one anymore when you use GLM. GLM unifies through a link function various statistical models, including linear regression, logistic regression, and Poisson regression. There are so many types of regression. GLM uses iteratively reweighted least squares method for maximum likelihood estimate. ML is stand for that one of the model parameters. That's how you're going to estimate the parameters. We don't go to that part. So they are using some kind of iterative method to get the values. Yes, that's one thing. And they say very clearly, one thing I wanna clearly over here for you guys to get a clear idea about this one. This one, that one. 1 second. I can put the right. This is very clearly something that you can see. So, can see. Look like it's in space. It should be somewhere. I show that one, it's gonna be very easy for you to get a clear idea. So mainly, this one has some kind of in general linear model. As I said earlier, it can tackle pretty much any kind of a regression model. Linear, non-linear, any kind of a regression model. Okay. Let's see that part. Okay, that's okay. It's not a big deal. Okay, that's okay. So see? So that's another way to have a look at it. See, okay. This generalized linear model is a way of unifying various statistical models, including linear, logistic, and Poisson. John Melda and Robert Wedderburn proposed an iteratively weighted least square method for maximalized estimation for the model. That means you can remember expected value of y given x. These are in that matrix format. Don't worry about that one. They say that instead of you use the mu, they prefer to use something called the function of mu. Function of mu. They were using a function of mu. That function of mu based on the function of mu. Okay, based on the function of mu. Okay, so it should be what's that one? It's not here. I don't know why it's not clear. General linear model consists of three components. A random component, see, expected value given y given x. Linear predictors, see, you know, b naught, beta 1, x1, beta 2, x2, all the way to beta k, this one. This transformation, you can use anything for x. Transformation, polynomial, dummy, indicator, interaction, anything. You see, can you remember we talk about instead of just putting just x, you transform. Can you remember instead of this one, you can put the ln x1. Instead of this one, you can put the 1 over x1. Instead of this one, you can say x1 plus x1 squared. Transformation, polynomial, and x1, if it is a gender, you can say that they will be that represented by 0 and 1, or that male, female, or that like that. If we have three languages, can you remember? With the aid of language, regions, with the aid of those steps, anything, and dummy variable, anything you can do that. That's the one thing. You have a random component, you have a linear predictors, and the third part, you have a something called linear function. Look at the linear function, link function. It's a function of mean. Function of mean. If the function of mean is mean, then that's type is. This is a link function. It is equals to expected value of y given x. See? Same thing. The function of mean. We are not tackling function of mean equals mean only. So far we did that one. So far we did the simple linear regression and multiple regressions. Gonna come under that one distribution type we are using. It's a normal distribution. The type of link function is called the identity because that mu, GM mu of a function is the mu. Instead of that one, you can use the log. See, function of mu is log mu. See, log mu. You not use the expected value of y given x for the one side of that your equation. Okay, I'm talking about one side of equation. You are using see log. Such a type, then the type of your link function is log. In such a scenario, you are supposed to use the Poisson distribution. Poisson is a discrete distribution, heavily utilized for that random arrivals, see, random walks, those things. The certain period, the certain number of that, even in the biomedical research, they were used heavily that how that all the germs that spread out within a given certain period of time, say given certain area within a volume like that. See? So that's called a Poisson. Poisson and its counterpart, exponential, they go together, twins. That means for exponential function you are utilizing in order to talk about the arrival time. First arrival. Let's say that number of people who are going to get into a certain area, or number of people going to get into the bank, restaurant. Okay, you observe that one that can be easily tackled with the Poisson process. It's called the Poisson process. So when you go to that one and say certain number of people came to that particular restaurant within a given certain period of time being handled by the Poisson. And at the same time, you can talk about inter-arrival time. First person came into that first customer to the second customer at that time period, and then that second one to the third one, that period. All these periods gonna fit in into some distribution called the exponential distribution. Exponential distribution means that is called the memoryless property. Mainly, it has a memoryless property. That means you have experienced that one. When you are, let's say that you're going to go to a certain place to that, let's say go to a bank and you're waiting in your line until your turn comes. Very moment that you had been that staying over there 1 hour until that you're going to get your chance to being served by that teller. When that particular time comes, the very moment you walk into the teller, you completely forgotten that you had been in that line for last 1 hour. That's called the memoryless property. That's why the big corporation run based on that kind of like a properties utilizing, because of that one, when you walk in over there, all of a sudden you've been given like a service, you're so satisfied, or sometimes not satisfied with the some under some circumstances, but most of the time with that one, that's why you completely forgotten how long you've been in the line for before you've been served over there, because of that reason. Like when before we're going to get a graduate, we don't, once you graduate, you cannot remember how long that is. A memoryless property. So like that. Okay, it's a big property. It's a memoryless property is come along with that exponential come along with the Poisson. So that kind of a distribution you can. But if you use the inverse, that's the inverse link. Then you have to use something called the gamma function, which is right skewed. This is discrete. Okay, this is discrete. This is well shaped. And the other one is you're going to take the log of what? This is nothing but what? Odds. See, mu divided by its counterpart. See, mu divided by its counterpart. These are odds. The log of odds called the logit. See, logit. Logit definitely that transformed by the logistic regression. You know that. That's why we are using logistic regression, because of this reason. Mu divided by 1 minus mu. That's the same thing that we did yesterday. 1 minus at a certain point that I showed you that how they were, sorry, this one, can you remember? We had that one at a certain time. Logistic regression, when we were talking about logistics. Yesterday. That's the same thing. Okay. That instead of I just tackled the P over Q. Here now you have a mu. See, mu, P over 1 minus P. Same way you have a mu over 1 minus P, logit. And then you use the what? Logistic. Log P that utilize that one. And then later on with certain transformation, the transformation not on this one, but yesterday I showed you. Yeah, here. It was a different page. Like that, and came up with this formula. So the same way here, we use the logistic and binomial distribution for y. I'm talking about y, or 1 over mu squared. It's called the inverse squared. Then you use the inverse normal distribution. All type of regression can be tackled by that one. That's a big advantage of that one. In addition to that, the GLM, there's something called the analysis of variance. ANOVA come along with that one. Okay, we can do the comparison GLM, ANOVA, and ANOVA normally utilized when you have a categorical variable for X variable, X axis. This one tackle anything. It's a major one with the category. Okay? whether you're Y variable or X variable, categorical, numerical, doesn't matter. Anything being tackled by that. That's how you come into the logistic regression, inverse regression, log regression. See, log regression. This is logic regression or logistic regression. See, logistic inverse regression, identity regression, which is the one that we've been using so far. Okay, we utilize that one in the large scale. So that's a GLM actually, that based on that, mainly that's the easy way to that data. That will be from the link function. You don't have to worry about this one. So you can tackle that one. I have some kind of a nice article about this one. See, reg GLM ANOVA. See which one and why and how. See, I can that upload this one to even that this can not the canvas to the Brightspace or to our course website. Then you can have a look at it. That one under that student resources or somewhere I can upload this one. So we can use the reg. We can use the ANOVA, analysis of variance. Variance. See, ANOVA GLM. So let's look at our number 4 or final exam. Let's get to the final exam. Okay. In the final exam, they were telling us to just use any data set of your own. I'm trying to use the same slip data, okay, for my convenience over here. Let's go ahead and get the slip data. See? Slip data, you can remember. See? We had this kind of that categorical variable. See? You have a male, female, English, French, other than others, and then they should be definitely converted into the numbers for a certain reason. For a reason to in order to run what? Reg and GLM, not for ANOVA. ANOVA you can just try tackle the way that it is over there. See, wages equal to gender. See, by the gender. ANOVA. See, wages over sex, and that if you want that you can even add that one. And on the other hand, is here under that one. See, fact analysis, principal component analysis. Let's see. Miscellaneous. Let's see chapter 2. This one. Final homework 4. Oh. Inform eigenvectors is a homework 4. Let's see that there are chapter 10. Fact analysis. We explained that one. Factor to principal compound of that one, logistic everything. Okay, that's a homework 4. And especially final exam based on that one. See, regression, you can wages and gender. Wages and gender, and then language reg too. See, you can run that one using gender, graph invariable, predict wage, gender group invariable, gender group invariable, gender group invariable. Here you don't have.
And can I ask a question?
First go with the same, then go with the double, same thing. Okay. So let's say that.
Do you hear me?
This one, see, you can run that. With the regression. Okay, go ahead, Angela, go ahead.
Hey, so when we're doing things, I just want to make sure that
I'm sorry, I cannot hear. I just turn on that speaker. Okay, sorry.
Sorry, I just want to make sure that I'm understanding this correctly. When we're when we're labeling the genders like male or female, then we're using them in a linear regression. If we're not seeing any, if we're not seeing like positive correlation or like high explanation, then it's kind of fair to say that there is no difference between the groups. If we're not seeing a difference between like the ones and the zeros, a clear difference.
Yeah,
It's like a different way of it's like doing linear regression, and if there's clear differences, like if we see a high impact by gender, we know that the gender variable is like significant, right?
yeah, you can see that one graphically. Can you remember in the very beginning from that scatter plot matrix? You can see that one. If it's not
Yeah, for sure. I just want to make sure that when I'm writing it out, I'm saying
right,
it in
right.
the right way.
No. You are on the right track because that's the one that we observe in the very beginning. You observe, visualize first before we're gonna go to the programming or mathematically get this done. That's why we're gonna just run that matrix first and then have a look at it and say, hey, that how they were related, how important to that gender to explain that variation of that. Sorry, what's the
And while we're like talking about um while we're talking about like explaining things verbally, I've been when I see a significant p-value and but there's still like some like 30% r squared, so like that means that we're like there is a relationship but it doesn't explain a lot of the variation, right?
No, not that much. R squared has like a serious issue because now we are with like a very advanced procedures we have. Can you remember CP, Mallows, AIC, the SAVA, so many other criteria we have. What's going to happen that I made it even yesterday very clear because the R squared going to go up. The more variables you're going to throw to the model, R squared systematically go up to a certain point.
Yeah, but if there's only it like let's say it's like line 20 where it's wages equals gender, and if gender has a low p score under 0.5 but there's like a 30% variation, how would you explain that? How what's the best way to verbalize those results? Like the relationship is significant but the gender doesn't explain a lot of the error in
No, not the error. The wages.
or variation in wages, variation in wages.
Variation in wages. This is the key part. What we are
Okay,
trying to
so
do.
it those I guess I'm just want to make sure that those two things can exist at the same time, and that's not weird.
Yeah, those two can. I mean, like these both can be exist too. The language and how could they see? These are multiple now. See, multiple. I'm
Uh-huh.
trying to explain through the gender and gender, education, age. All these would explain the wages. Is there any way that how could that any differences? See, age differences would tells there differences in age wages or not. The education level differences would say that changes in that differences in wages. Overall together, all of these can explain variation of the wages at the same time or partially. That's why we have a single test. You can run that single test. And as you said that you're going to go ahead and look at the p-value of age and say, oh, what I'm going to explain with the p-value of age. That means you're going to say whether with that age will not explain the variation of wages. That means it's not significant. I mean, like you can take it out, but we are not at that stage to take it out because we have other procedure, very advanced procedure called the backward elimination, stepwise elimination, the procedure, and forward elimination. You have to move on to those the procedures. At the end of the day, the best 5 I have already listed over here. Best 5. See, can you remember? Under certain I listed these are the best 5 procedures, not the p-value, not the r square. You at this stage, these are the one you looking into. These are the major 5, or you can add more. All these are the one that you looking into at the end of the day to come up with the best model. Not simply not the p-value, not the simply that single that sorry the individual testing or partial testing or that overall testing. They would not produce the best because that those are that in the primary stage some kind of like a the base, the foundation for us to use this kind of a method. We are using that foundation to move forward. But later on, people very recently they came up with a very powerful procedure How could we know these are powerful? Because they were based on the mathematics, they were based on the data, they were based on the prior knowledge, they were based on the so many that repeated measurements. So many things being involved in that one to that verify this gonna be the best one. So these are the one we're gonna utilize. So at the end of the day, when you that let's say working for a company or that you're gonna start your own company at the end of the day, your client walk into your you bring some data and you want to analyze and data and say that okay, we're going to analyze based on these criteria. These are the best models. See, even look at the stepwise model is the best model by stepwise with the SLE 0.20 and 0.10, not 0.05. 0.05 not. It's not a good compromise between the power and size of the test. So many things involved with this one. I think that because of within this short period of time, we cannot go through that one, but for get a basic idea, go with these ones, not even with the individual ones. Individually, that at this stage, individual one doesn't play any role. That I would say that oh, wages will be explained by the age by looking at the p-value or r square. No, they were that nothing compared to that very powerful that procedures like them. See, but you can when you write, you can write and say, oh, individual testing. Through the individual testing seems like age is not explaining variation of this one, but that age will be again added if you go to the different kind of a method like powerful method like stepwise or backward or forward elimination procedure. We saw that one. Whatever that's the best thing about that this other procedures rather than that you taking this and the other there's another method, all possible regression model. So many procedures come together at the end of the day. But out of all these methods, those 5 methods that I showed earlier are the one that you have to that stick to. But there's no any that very strict rule that okay you have to stick to this one. No, like that. Sometimes that if you feel like okay with the aid of p-value, if I can make a decision, go ahead and do that one. But you have to this give the backup support for that one to say why I'm using the p-value only when I know other methods. Right? The similar fashion, the same thing here. You can go individually, age, education, gender, and language, or you can go 2 at a time. That's called partial testing, or you can overall testing. When you go to the overall testing, that is you can say all these not going to play a heavy role of explaining the wages versus its counterpart. At least one of them can explain. Which you don't know which one was there. Then you don't know which one. Then you have to do the something called the multiple comparison. Those comparison we don't do in this class because those are multiple comparison. But when you write that one, you can write any way that you want. But it's all about that you say that okay, you feel like you don't want to do those tests. I'm going to stick to this one, and based on whatever I see on the printout, I'm going to write in this class. That's okay. Whatever, yeah. If you want to do more rigorously, then do like the way that I have done over here. This is all for that you to. This is for your the very heavy knowledge that at the end of the day, these are the very good stuff. At the end of the day, you have to utilize. But if you write that something that based on p-value or r-square, no, that's okay too. Okay, so discussion is kind of like something like that. Okay, so here we can get this done using see. I'm sorry, here that first I'm gonna write with that individual gender only, and see later on I added this one. See, I can say run this one easily. You can run. See, you know that one. So those are basic way of doing that one. Such a long time. Oh no. Why? The regular equation. Say that you can go with this one and say that the gender, see, gender, see, significant. That means gender is a key role. We do not take this out. We keep that one. But we don't know whether this is going to be that much important to that produce that explain that variation of the wages, because that we have other method as well. But for time being, by looking at this one, if you want to make the comments, if you want to write, just write it based on this one. That's okay. That's fine. You don't have to run all other methods. But if you run, you get, next step, you have to go to the all possible one. Then you have to go to all the criteria that I explained, stepwise, forward, backward, and then MAP, MAD, that press, AIC, SAVA, all these. Okay. So the second one, I can get this one using the GLM. Then when you run with the GLM, you saw that what are you going to get. We had that very broader discussion on that, on its output. See, can you remember type 1, type 3? We discussed this one in large scale. See how they're going to be add to this one. See, can you remember? You can remember these two. See, sorry, they're not these two. These two. See, 114. Here, type 1 and type 2 gender only. See, since we have one, see, they should add to this one 11492. See, 11492, 11492. See, if you have a 2, 3, 4, and later on you can see their summation in type 1, they add to this one, but type 3, no, you know that one. Those are called the sequential. We had that broader discussion. See, we still can get that pretty much the same results, but with the, like some extra tables. Now you go to the ANOVA, analysis of variance one. You go over here, you have to say the class. You're going to do by the gender. Okay, do by the gender. Wages being explained by the gender. See, gender is categorical. Gender is categorical. Let's do this one. ANOVA proceed. So model 11492. I want to see. It's the same thing we got earlier. We're going to run all these three together and then see if they produce the same thing. Come on. One one four nine three. Regression model using group gender grouping variable predictor regression procedure. 11493. 11493 using the GLM procedure. See? ANOVA procedure. 11493. See? All these three methods. See, this is the way how they're going to set this up. You can see, tell this the gender. You don't have to say gender. You can go to call the sex, because the male and female doesn't matter. You don't need the number when you run the ANOVA. You don't need the number. Those are the. This is nothing but the group. This is nothing but the group regression. The group regression. You don't need the numbers. You can go back. All these things. Then what I did was that I added that both of them. See, both of them. See, and see, let's age, pretty much everything. I'm sorry, not the both of them, not only the gender, age, education, gender, language rate, age, education, gender, language rate, using right procedure, GLM procedure, and OR procedure. 360. Rate procedure. 73 360 GLM procedure. ANOVA procedure. See, it's not the same thing. Not the same thing. What happened? 6 wages plus 6 and language rate, 6 language rate. Okay, we are missing something. Age model. See, so here ANOVA 1, you cannot add categorical. These two quantitative ones you cannot add here. Okay, that's the only difference. For the ANOVA is only for when you have a categorical regressive variable. You have a discriminant and classification, sorry, discriminant and logistic regression when Y is categorical. Okay, so wages, sex and language only is being class those two only. So that's why we have a different numbers, because those two we drop now. But here, this is, as I was trying to show that this will work if categorical work, quantitative work, but not here. The age and education you cannot add to ANOVA. Okay. In addition, that I have to tell you, there are 16 types of regression in data science: linear regression, polynomial, logistic, quantile, ridge, lasso, elastic regression, principal component regression, partial least square regression, support vector regression, ordinal regression, Poisson regression, negative binomial, quasi-Poisson regression, Cox regression, and topic. How to choose the correct regression model? If dependent variable is continuous and model is suffering from collinearity. See, collinearity means like a suffering from collinearity means like there's a correlation among the regressive variables. Or there are a lot of independent variables. You can try PCR, PLS, rich, lasso, and elastic net regression. See, PCR, PLS, see, partial least square, rich, lasso, and elastic net regression. You can select the final model based on adjusted R, R squared, RM is AIC, BIC from this one. Oh, so as I said that you can add other things to mainly these two play a heavy role, plus that stepwise one, okay, plus that stepwise, that one you can add to. If you are working on account data, you should try Poisson, quasi-Poisson, and the negative binomial regression. To avoid overfitting, we can use cross-validation method to evaluate model used for prediction. We can also use rich, lasso, and elastic method to correct overfitting issues. Try support vector regression when you have a non-linear model. So this is a very, as I mentioned in the beginning, that when you become like a data scientist, so with the masters, you have to move with the, like a PhD too. During the PhD, that when you take the classes and your dissertation and everything, you exposed to so much of material and procedures and techniques, and you can be very elegant and elite data scientist at the end of the day. Okay, but when even with the masters within this, the way that we cover a lot of material, because these materials are normally being covered within like 15 weeks. But we managed to cover, because sometimes in the 15 weeks, most of the instructors, they don't even tackle the most of the principal component. They never cover. They normally cover only the regression part and multiple regression. But anyhow, we managed to do this one because we do everything with the aid of this programming. That's the beauty of this the program, because when you have the programming, it's easy. You don't have to do anything by hand and wasting time. Just a little bit do, that's good, because that's why data science is the #1 that area across the globe right now. So that's the final exam. You can pick the data set and you can answer like that within those 3 methods. And homework 4, you pick a data set. You can do the principal component analysis, same thing that we did earlier. Okay, or principal component analysis, and then from the fact analysis, and then come to principal component, you know that procedure too. Okay? And the second part is multiple regression is not a big deal. Okay, let's go ahead and do this one a little bit again. So this one you have a GSP data. I got the GSP data for my convenience of principal component. And this one we did already under that one. It's not a big deal. Okay? So then see, in 5 it's been that reduced to 5. Okay, because through the Kaiser rule, see, okay, if you want, you can say equal 5. We did this one. We don't have to do that one. And we did this one even through the factor methods too, even factor methods too, through this guy too. No, not this one, not that example. Okay. That one. I want to make sure this one. I'm gonna separate it. See, I come back to this one. Print comp. Okay. Why we need this one? I don't need this one. This one. What is this one? Factor print comp. Okay. PCA. GSP. Okay. What I'm gonna do? I'm gonna get this one and then what? I don't need this one. Okay. I ran that one for you to see. Okay. I'm gonna get up to here and cut and paste above this one here. Printcom, through the printcom you can run this one. Through the factor analysis through you can do this one. You can do the adjustment through this procedure, and then you can compare with that one. I ran that one again for my convenience again. See. That's the principal component analysis. This example for principal component regression. See, printcom. See, here data has been given. That data is fitness data, has a, like age, weight, oxygen, runtime, response, run false. If you want this one, this data. See, principal component, see, fitness. This one you run this one, principal component analysis you can run. Okay, let's get the fitness data. Fitness data into the system. 31 rows, 31 observations, 7 variables. 4, 5, 6, 7. And then get the principal component analysis. You know how to write it down. Very nice thing. I can value the principal component. You write this way. This value minus this one. Blah, blah, blah. I have a 6, but if you go ahead and look at this one, see, only 2 will be more than enough to explain. See, you can go with the 2. First principal component and the second one. But if you go ahead and look at the how much it's gonna explain the variation, only 65%. If you want, you can go to the third one as well. Yes, this one. Third one too. The principal component regression. Now we're gonna try to do this. It says that there are 2 easy ways to compute principal component regression. Method 1. One is the PLS. PLS stands for that partial least square. Okay. PLS. PLS partial least square procedure. Least square. Can remember. Procedure. Oxygen see being explained by this one. Solution. Let's say on this one. Still, they're going to evaluate all the variables. All the variables, and then let's go to the second method and see how it's. Second method, you do the regression. plots none, see, outer C for the P, see, model, see, they're gonna say to omit, number of omit, how many to be omitted, see, and then print, and where they go to this one, and then you can see that, okay, let's see the regression, regular regression. You're gonna run the regular regression, see, oxygen, age, one time, this one, blah, blah, blah. Why? At the same time, I'm gonna omit two principal components. When you omit two pieces, you keep four by the second method. The regular regression procedure. But they have already taken out everything, and then it's gonna give you that the regression value. See, very easy with the aid of, see, with the aid of, see, this one. Then you go to the PE. I call this one, take this one, see, for parameter estimate. Parameter estimate, see. IPC stand for incomplete principal, sorry. Incomplete principal component. This one intercept, this one age, all these values. Did we show that one 127 intercept from this one? You don't have that one 127 intercept. Okay, let's go to this method. See, 127, but here, because it's based on the incomplete partial component, because we have taken out two because of that. In the full one, they come up with the thing here. In this method, they're gonna take into account. See here, even that you gonna say number of factors. See here, number of factors. PCR method, principal component regression, number of factors. Okay, I'm gonna run this one more time. But they're gonna evaluate the estimates for the parameters. See? 1, 2, 3. See? Number of exacted factors. See? So they are model effects. See? 42, this one. See? The effects. The second factor. Third factor. This is the total. See? It's a variation. It's a total. See? Here, dependent variable. See? Go along with that one. So, but they're going to calculate all that, that parameters, okay, parameters. But here, if you go ahead and use this method, like a regular regression. So, get a regular, so that all the information, regular information. But they have taken out two that regression variables. From that one, if you go to the parameter estimate, if you type this one, there type IPC, it's an incomplete principal component from the variance to max plus, see, variance to max plus. Those values you can see now through that procedure. Because it's incomplete, you don't have all the principal components. Max plus, they are estimates. B naught, B1, B2, B3, B4, B5, like that. I can pretty much run this, put all this together. This is not together. That's for the regression. Okay, that part they don't ask you to do, but I just added 3 extractors. It's not reg procedure. It's a partial least square procedure. Partial least square procedure. Reg procedure. 47, 37. See, let's say dependent mean. 47. See that these are the principal components. See, from the same percentage of variation accounted for by the principal component. Those are the variation. Okay, dependent variation, how much being accounted by the principal component. These are from the model effects. These are from the principal component. How much variation being explained by those principal component. These are the one with for the partial because that we are losing that 2 principal components over here. And all that we're going to come up with the same as at the end of the day. So the same way that you can run this one with the big data fact analysis as well. Fact analysis, that's principal. If you want, then you can keep that same procedure that I was doing over here. Fact analysis, that means if you have this one to here, copy, and then paste over here with data, if you're going to do that one. I'm talking about the principal component analysis. This is just the fact analysis. If you want to do that one to this one, then fact analysis, GSP. That's for the GSP. I don't think that we need that one. So it's for the GSP. Fact analysis we have already have over here. We don't need that one. We don't need this one. If you want that, what I'm trying to say, if you want that, you can do that. I did the principal component one, know that if you want to do the same thing for the fact analysis, date of the fact analysis for this one, that's what I was talking about. See, fact analysis to this one. So that part, if you are planning to do here, so then you need to go to the GST, that's the data. Here data name fitness. Fitness data. So okay, so go to this one, you can say fitness ES coefficients. Then you can say fitness coefficient, utilize and print. And this method, you're gonna get the fitness coef eigenvectors, you can see eigenvectors 1, 2, whatever that numbers that you are planning to keep. I think in this one we kept only 3. See, 3, we can say 3. Then eigenvectors. Then print count again, if you run, that's the same thing. And it was 5 or 3, doesn't matter. Whatever the number. And compare contrast. And the part 2 that you have a drug data and then regression, regular regression, scatter plot, drugs, and then use the not only this one, use all the procedures and come up with the best model at the end of the day. Use all of them, not only these 2. Stepwise, all possible. Then R square, adjusted R square, CP, RS, and this for the all possible one. Akaike, Hava, was everything that I was mentioning earlier. So that's the homework for, and the final exam pretty much. That's it, I think. So that's all that I think that we can cover. That if you guys have any questions, we can discuss something that you want to discuss. Something pretty much everything's covered. That right. So anything you want to? Sorry, I'm gonna put this mic on. Okay. Oh hey Thomas, yeah, go ahead. I'm sorry.
No, no worries. So I just wanted to clarify on the homework 4. It said option 1 and option 2. I just want to clarify, do we have a choice of doing option 1 or 2, or do we have to do both sections? Because
No. In the homework one, just okay. Let's go ahead and look at it. That one more time to make it clear. Okay. This one.
option 1 does the PCA or factor analysis, and then option 2 does the straight regressions,
Yeah. No.
and
Okay.
then forward or backwards.
Okay. This one option. That option 1 and option 2 means like either one of them. No. You don't
Okay.
have to do both. No. Just
Making
one.
sure.
See, that's 100 points. It's not being split either this or this. If you do the PCA, you don't have to do this one. No. Either one of them. Okay.
And then we were covering, the second question was, we were covering the split and testing. Were you just kind of teaching us that, and that has nothing to do with the actual assignment itself?
Which one?
The split and testing?
Oh no. Splitting and testing, those are there. No. I mean, like if you want, you can use that one, but if you feel like that it's not a part of that one, I added that one day, that when you down the road, if you want to do the data analytics, it would be utilized, and one day you can recall and say at a certain point we cover that one too, like that. Other than that,
Yeah.
you don't have to go in that route and then give the answers. No.
I just want to clarify that, because I know we were learning it, but I didn't see it sort of as a task to do in the homework, or seeing it in as you're covering the homeworks and everything. So I just want to clarify that. Thanks.
Yeah. Because the homework for that, simply that it says this is, you can see very clearly that homework for anywhere that we don't talk about that one, but that for here it doesn't even say very clear, because they were talking about the selection numbers, selection procedures, only stepwise, backward, forward. But what I did was I added some new procedures. Those are the very powerful procedures I mentioned even when I was answering that. Angela, I was telling that when, can you remember under this one, see, these are, see, at that point that I was just mentioning that, see, this one actually data splitting come here after the data splitting, new 3 quantities being evaluated. See, you don't have to do that one. No. These are, you don't need, see, but you keep in head. But the textbook has all these already, but you don't have to go this route and do, because simply you give the selection procedures only. Stepwise, backward, forward, that's enough. And the all possible one, that's more than enough. These are, but keep in head, these are the most powerful ones. If you want that, you can use that one. If you don't have to. CP1, we saw that at a certain point, but press SBC, AIC, you don't have to worry about that one. Okay. Any other questions? If you guys don't have any other questions, I can wind up over here. It was so pleasure to doing a class with you, and then I hope that down the road we're gonna meet again, and then you guys I might gonna teach a different kind of a class, and you gonna take those classes, and then we can meet. I really enjoyed that teaching this class. I'm gonna teach again in December too. I'm gonna take a 1 month break because I have another big job, because I have because before I leave, I had to tell you that because I'm looking for the 2 data scientists, because I've been appointed as the dean of one of that university back in my country, but I operate from here, do everything I do from here. But in the beginning, we need some 2 data scientists. I'm eyeing for 2, that the people who has either PhD or master's, so who can teach data analytics classes, pretty much like the basic classes, like the classes that we are covering right now, plus that we added machine learning, Python, that neural networks, those kind of classes. But if you guys have any interest, or if you have, because you have to teach through Zoom only. There's a 9.5 hour that time difference, plus we're gonna pay $100 per hour, US dollars. So that's not. So if you're interested in, just let me know that that part too. Okay. So if you don't have any question, I'm gonna let you go. You guys have a good night, and then stay safe and be well. And then I'm gonna give you whole next week for you to go to finish pretty much everything. And then I'm grading that homework number 3 too. That then you can see that tomorrow I'm gonna put the grade for that one. And then see you another time. Okay. Good night. Have a great day. Take care.
Thank you. Bye.
That's good. Thanks, Professor.
Thank you very much. Thank you. Take care.